Welcome everyone. So in this short video, I'm going to address the idea of limits and continuity at a given point, okay? So imagine I have a function f defined everywhere. I put two arrows, so imagine the domain is all reals. And what I'm interested in is, I'm interested in figuring out the limits as x approach a in all the examples I'm going to deal with. So notice that f of a doesn't exist. So I put a hole here. So if I say what is f of a, you don't say b. You just say it doesn't exist, right? However, I'm interested in limits. So if I take a limit as x approach a of the function f at x, that limit is b. Now, whether or not this point here is filled or not filled, the limit does exist because the limit is a. So if I approach a from the left, the limit is b. And if I approach a from the right, the limit is b. And limit has nothing to do with whether or not the point is in the domain. Does that make sense? So the limit here exists, and that limit is b. Okay? So now let me give you another example. And look at this curve, this function f. And again, I'm interested in this value at x equals a. So if I approach the function, if x approach a from the left, and that's what it means, left limits as x approach a from the left of the function, that limit is b. Okay? Now, whether again this is a hole or a solid dot, it doesn't matter. If x approach a from the right, that limit is c. So I did get a limit from the left, I did get limits from the right, and for the limit to exist, the limits from the left and the limits from the right have to match. Not only that they have to be real numbers. So you get like 5, 5, or 20, 20, okay? If you get positive infinity, they do match, but they're not real numbers. So we would say the limit doesn't exist. In this case, b is not c, so the limit does not exist at x equals a. Okay? So for the limit to exist, the limit has to be a real number and it has to be unique. I got two different values, so we say the limit doesn't exist. Okay? So now, what I'm going to do is introduce the idea of continuity. So let's begin with the limit again. I made it solid now. Limits from the left as x approach a is b. The limits from the right as x approach a is also b. Again, whether this is a hole or not, that limit is always b. However, if I ask you what is f of a, in here, f of a did not exist. There is no f of a. F of a does not exist. But in here, f of a is b. So we know the limit exists. Why? Because we got one single unique real value. And f of a is b. If the limits at x when x approach a matches f of a, we say the function is continuous at a. And this is exactly what I'm saying here. So if the limits as x approach a of the function is exactly the height of the function at a, then we say the function is continuous at a. Now, visually, you know that this function is continuous in the entire domain, but that's not a good enough reason or proof to say that the function looks continuous at x equals a. You have to demonstrate that the limits at x approach a matches f at a. And this is a mouthful. Watch what it says. When I say the limits as x approach a of f of x is a number, this is a number, it means the limit exists. And what it means is the limit from the left matches the limits from the right. That's what this means. But not only that they match, that matching value happens to be f of a. So if the limits from the left and limits from the right is b, and f of a is c, we would say the limit exists, but the function is discontinuous at x equals a. So this is really a mouthful statement or equation. Now, Notice here, the limit as x approach a exists, but the function was still discontinuous. Clearly here, the limit doesn't even exist. In here, the limit as x approach a does exist, and also f of a is the same value, so we say it's continuous. What it means is, if a function is continuous, clearly the limit has to exist. Think about it. If a function is continuous, the limit has to exist. The converse is not true. Just because the limit exists, it does not mean that the function is continuous. Here is a great example. Okay? The limit does exist, but the function is not continuous at x when x approaches a. Now, so when you have a statement that is true, the converse does not have to be true. Sometimes it is true, but in this case, it's not true. So if the limit doesn't exist, it does not mean that the function is continuous. It might, like here, but it doesn't have to. However, the contrapositive, if this is true, the contrapositive is always true. So let me pause for a second. So imagine I have a statement, if P, then Q. Let's say that is a true statement. The converse says if Q, then P. Well, this is not always true, so we call it false. The contrapositive always matches the original statement. If not Q, then not P. If not Q, then not P. This is called the contrapositive. This is called the contrapositive. So if this is true, this has to be true. If this is false, this has to be false. This is not dependable. So what it means is, if you negate Q, then you negate P. That's the contrapositive. So let's apply it here. We know if a function is continuous at x equals a, then the limit has to exist. The contrapositive says if the limit does not exist, then the function cannot be continuous, and that's what I wrote here. If the limit at x equals a does not exist, then the function is not continuous. And finally, let me just visualize the whole thing for you. So imagine you have two concentric circles. So continuity is more demanding than limits. So if a function is continuous, if let's say you live in this circle, then you clearly live in the big circle. Which means if the function is continuous, then the limit has to exist. However, if you live in this big giant circle, it does not mean you live in the inner circle, because you could be here. Which means if the limit exists, the function might be continuous, but it doesn't have to be. Let's say you're here in red. The limit exists, but the function is not continuous. And the example I showed you is this one. Okay? The limit does exist, it got a real value, but the function is discontinuous at x equals a. So I hope this is helpful. Okay? So this is the relationship between limits and continuity at a point x, at a particular value, an argument x equals a. And continuity is more demanding than limits. Look at the contrapositive, and I'll conclude. If the limit does not exist, then the function is not continuous. It should make sense. If you are not in the big circle, there is no way you could be in the smaller circle, right? Because the smaller circle is in the big circle. All right? I hope this is helpful. Take care.